So it seems we are live, and today we are doing another day of Advent of Code. We will do day 5, and I will also do review of day 4. I did it on my own. Day 5 we will do in Rust, and day 4 I did in Julia because I felt that last time I did, I think it was day 2 with Julia, I was a bit slow, so I wanted to practice a bit more. And actually the task was really matching. So let's start with the review, and yeah. I won't spend too much time today reading the task for day 4, but essentially you get a list like that. And in that list, you have each line is a pair of elves, and each of those entries separated by a comma is assignment, range assignment, essentially. So 2 to 4 means 2, 3, 4. 6 to 8 means 6, 7, 8. And the first part, you need to find all cases where one's elf assignment is completely inside another's elf assignment, like that, for example. And in the second part, you need to figure out how many overlapping pairs are there, I think. Yes, exactly. So just the number of pairs that overlap. Now, in Julia, to do that, as usual for Advent of Code, the most complex part of this code is actually parsing the input. And here you can see that we need to do some funny stuff with it. Let's maybe run it in REPL so it's a bit easier for you to follow. So here's our input that we read from file. As usual, we have day 4 assignment here. And you can see that then we can parse it to parse input function. I will just execute it line by line so it's a bit easier for you to follow. First, of course, we split it into lines. Then we split each of those pairs of ranges. So now we got a vector of vectors of strings, essentially. Now, what we can do, we can put this into a matrix. And here the syntax in Julia is a bit funny. I haven't found a better way to do it except for using like reduce. But essentially, we do horizontal concatenation, and we splatter the input vector into like multiple arguments. So it looks like variadic function. And then we transpose it. So if you do that, you can see we get now a matrix. Of course, in Julia, the best thing is to work with those matrices. That's what language is made for. So the next part that we do, we can also parse each row. So we do that. And notice that in Julia, of course, you can apply a function. You can just broadcast a function across an array. So that's what we do in here. We still use map for like the most external part of this loop, but otherwise we first split each of the rows by this symbol, each of the entries, and then for each of element of this sub vector, we parse it as int. Now, given that input, what we do next is the key to the solution. We transform this 2-dimensional matrix of vectors into a 3-dimensional array. So I didn't find a better way to do it as to create a 3-dimensional array at first, and then essentially iterate through each pair, through each elf, and then through ranges, so lower and higher part of each range, and then just essentially assigning the value we extracted from our input here. So if you do that, we will get this thing where we essentially have 3-dimensional array. Now, when you work with 3-dimensional or like 4 or whatever, more than 2-dimensional arrays, it can be quite confusing. So what I suggest always is trying to think about them as coordinates. So essentially you assume that in this case you have 3 variables. You have the pair ID, so to say, so the row of your input. Then you have 2 elves, that's your second coordinate, 1 or 2. And then for each of those elves, you have a range, which can be lower or higher part of this range, which also gives you a third variable, which can also be 1 or 2. So for example, if I want to find the first row, first elf, the lower part of the range, that's the coordinates. And if I want to find the higher part of the range, that's the coordinates for it. Now, if you look at our input, you can see that that's exactly what we got. Now, if I change the middle coordinate, you can see this is our second elf, lower part, higher part. And of course, then you can change this and get the next row values, etc. Now, given that representation, the task becomes very, very simple. So in first part, we just need to ascertain how many rows we have where one pair is completely, one range is completely inside the other range. Doesn't matter if it's first inside the second or second inside the first. So here we can just use this function. And what it does, it essentially iterates through all rows, and it selects the lower part of the first elf, and it checks that it's less or equal to the lower part of the second elf, and at the same time, the larger part of the range for the first elf is larger or equal to the larger part or larger boundary for the second elf. This is in case the first elf's range is fully contains the second elf's range, or we do the same exact operation, but now we switch 2 and 1 essentially. So we look if the second elf's range fully contains the first elf's range. And then that will give us, let's execute it and see what it will give us actually. So it gives us a bit vector, which in this case, maybe I will even do it like that to make sure that, yes. So we got a 1000 element bit vector. And now those ones are just essentially true and zeros are false, so we can find the number of rows by just summing them up. And that gives us the solution for the first part. So then when we do this, you can see we got this solution. Now for the second part, the task is even easier. Here we just look that we kind of do it in reverse. We first look that ranges do not overlap. We know the total number of pairs we got. So we can assume that all pairs where ranges do overlap, we can find by taking the length of the input minus non-overlapping pairs. And to find non-overlapping pairs, we again use those broadcasted operations, broadcasted comparisons, essentially checking that ranges do not touch each other. And again, we write the first part, and then we just copy it and we switch 2 and 1s, and that gives us both combinations. So by doing that, we can execute it, and we also get the solution. And as before, I also added here a nice assert and show macro, so we can see we can essentially do this. And that's our solution. Now, that being said, let's create a day 05 thingy. Of course, new. So now we got our Racine set up. And let's verify that we can execute it. And let's look at the task. So this time, let's check first what our input is. Oh, I see. So this is one of those tasks where, again, parsing the input probably will be the hardest part of the task. I guess looking at this insanity, my approach here would be first just making sure, like maybe we can just encode it manually at first, and then we can do the proper parsing as a bonus. Yeah, seems like a better option. We can parse the rest of input normally because that is way easier. But let's read it and see what it says. The expedition can depart as soon as the final supplies have been unloaded from the ship. Supplies are stored in stacks of marked crates, but because the needed supplies are buried under many other crates, the crates need to be rearranged. I guess that's the whole this thing. The ship has a giant cargo crane capable of moving crates. To ensure none of the crates get crushed or fall over, the crane operator will rearrange them in a series of carefully planned steps. After the crates are rearranged, the desired crates will be at the top of each stack. The elves don't want to interrupt the crane operator during this delicate procedure, but they forgot to ask her which crates will end up where, and they want to be ready to unload them as soon as possible so they can embark. They do, however, have a drawing of the starting stacks of crates and their rearrangement procedure, your puzzle input. For example, blah, blah, blah. So in this example, there are 3 stacks of crates. Stack 1 contains 2 crates. Crate Z is on the bottom and crate N is on the top. Stack 2 contains, so this is bottom, top. Stack 2 contains 3 crates, M, C, D from bottom to top. And finally, stack 3 contains crate P. Then the rearrangement procedure is given. In each step of the procedure, a quantity of crates is moved from one stack to a different stack. In the first step of the above rearrangement procedure, 1 crate is moved from stack 2 to stack 1, move 1 from 2 to 1. So that means it will become D and Z, CM. Exactly. In the first results in this configuration, the second step, 3 crates are moved from stack 1 to stack 3. Crates are moved one at a time. So the first crate to be moved, D, ends up below the second and third crates. Oh, this is interesting. So D and Z, essentially, are moved from stack. Then again, because I moved one at a time, finally, they'll just need to know which crate will end up on top of each stack. So you could combine those together and give the elves a message. Completes what crate ends up on top of each stack. Okay, so let's copy our magical input. Four, 9, 8. Always doing this check. Exactly. Okay. No, it's not JavaScript, it's plain text. Thank you very much. Now, let's try to figure out how do we want to encode it. So we will need to do a lot of those movements. It's like 500 operations. I would imagine that if we try to do it naively, like having a bunch of vectors and actually moving stuff, that will be very slow. Instead, we probably need to... Actually, why? Well, we can pre-allocate the whole thing and just assign it, but that will be pain. Okay, let's not overcomplicate it. Let's maybe just make the... let's make some kind of a struct for that thing. So let's say crates. What will be our main thing here? Oh, I think we can actually try to do we can try the const generic thingy, right? So we can say n will be something like your size. And then we will have, say it, state, whatever, not very inventive name. What will be those? They're just letters. So it will be char and the size n. And I think, oh yeah, I'm messing up the syntax, I think. Yes, that's this thing. Can we like do a bunch of derive, let's say debug, let's say copy. Can it be copy? Am I missing something already? Oh man, of course. I'm messing up my syntax again. Okay. No, it can't be copy. Okay, then just be clone. And let's make it pop because we don't care. So that's our state thingy. We can already try to do test. So let's do this. Hope it's not too small. Yeah, it looks okay. And then we can do representation test, something like that. Then, of course, say, yeah, assert equality. Let's just check that our tests fail. So do cargo test, failed. Cargo test doesn't fail. Magic. Okay, let's try to encode our test representation here. So let's say it will be, oh, and I already messed up, right? It's not a char, it's a vector of chars. Man. Yeah. So let's say test input, and that was creates. Can I do it like that? Probably I cannot do it like that, right? Let's make it into a function. Test input. And here we can say state is then let's copy this in. So for the first one we have vector bt, actually in reverse, right? Z and no, if it's stack, we can pop the, okay, yeah. We do it like this because vectors in Rust can be used as stacks. So we can pop stuff from the top of it easily, which is good. And this will be M and this will be C, right? And then of course we can also do stuff like just reverse it when we implement the actual proper input. But now we do it like that. And yeah, that looks good. And then we also have a bunch of moves. And moves, let's parse them. Oh man. Okay. So you'll just do like a vector of strings here. Right, right. And that thing. And then we kind of get test input. Oh. Creates and moves. So, and of course now, yes. Okay, that looks good. Let's add function for parsing moves. And what will be our moves thingy? Moves will be, it's like also struct move. So from, it will be like usize, to usize, number, how many of those to move. Let's say also usize, I guess, for now at least. And we also add all the typical derive, debug. Well, this we can do copy as well. Now parse move will return us a vector of, you guessed it, moves. And what does it accept? It accepts string. Actually, let's maybe make it into a string then so we can test it. Hold on. Right. Do the Come on. What is this? Why are you not happy? Okay, time to look up syntax. How to multi-line strings Rust. I definitely remember that it could do it. Oh, you can just use the, okay. So it's like that. Oh, I think I understand. I probably even need to do it like this. No? Found struct string new. No? Okay, can you save yourself as just like literal? Okay, it can. Okay. Then this will be, and of course then you're not static, you are owned. So moves string. Yeah, we can do all this stuff like dereferences to reference to str, but we will not bother. So given that, let's just stream it just in case, and then we can do split. Let's split it by n. And then, yeah, of course. By the way, this is a trick I always use when I'm annoyed about it showing me errors while I type. So we split it, we got now lines, right? For each line. So let's call it row moves. Let's call it moves, and let's make it into a vector, and let's then make this into, that's what our return thingy is. So for each of those, we need to do, we essentially can do just split ASCII white space. This will give us a iterator, and then we can just, so we can do, this is very hacky, but it's, I think, the fastest way to do it. So we skip the first thing. We then take the, this is from, no, this is number. We say it next, and then we, this should return stuff, right? It returns us option. Yeah. Next, we need to, let's unwrap it. Also, don't care about this for now. Unwrap it, and then we parse it. How parse will work? Example, parse as size. And this, oh, it doesn't even, I expected it, it should return result. Is it, yeah, unwrap option. Of course, iterator should be mutable. So that now, okay, perfect. Then guess what we do? We skip the from thing, and we do exactly that thing, but this time this is from, and then we repeat this whole thing, and we say to. And that's, and then we can say moves, push, move from to num. Ta-da! Or not. Cannot borrow moves as mutable. Of course you can't. Okay, now that looks more reasonable, and we can try it out. We can say Well, in this case, it's not even a test, right? We just get parse moves, 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 and this is vector of move. But parsing test, maybe even test input parsing test. So creates, and this will be moves equals get test input. And then we can see if moves, we can just debug it at first. Now, by default, if I run it right now, nothing will be output. Why? Because we are capturing output by default. Let me show it to you better like that. You see? So to not capture output, I think that's the way you do it. Exactly. So we can now see that our first move from 2 to 1, 1. Second from 1 to 3, 3. Okay, good. So we can just look at this. First, the things we can say assert equal moves length is 4 and assert equal moves 0, and here I say move how many num, it will be probably reference, so 1 from 2 to 1, and then we can assert that 1 is 3 from 1 to 3, but let's keep it like that so we can see that stuff is failing. What don't you like? Binary cannot be applied. Of course it cannot because I didn't derive it. So let's derive it. Let's say partial equality, equality, and now expected struct move. But I don't want to move this stuff out of the array, so let's do this. Good. So now those two should pass, that should fail. So exactly from 1 to 3. So now let's fix it. Ta-da! Everything works. Okay. Now that being done, let's start is writing our test for part 1. And let's implement the actual movement logic. So actually let's do move function that takes a reference. So creates reference to creates, mutable reference to creates actually, and moves will be a immutable reference to moveset. Oh man, vector of move. And what does it return? Well, you know what? Let's not destroy it. Let's keep it like that. It returns a new crates thingy. That looks good. Oh, move is a reserved word in Rust, right? So let's call MV. I don't think it's actually used. I think it's just reserved. So we do move, and then we, for each of those, we essentially, let's hide our parsing thingy. Let's create new crates as well. Clone, so we don't worry about destroying stuff. you have a copy of them now. State vector. Oh, perhaps we can even make it into implementation function on the create struct. That will probably look a bit nicer, but for now let's stick with that, because I'm not sure if in the second part I will need to maybe to keep the original struct or if I will need to copy it. No clue. So for now I'll just do it like that. So they are stored as stack. We will not bother with any optimization. We will just say for in num. So depending on the number of things, the number of crates we need to move, we just execute it the same number of time. Of course, you can take slice, do like the whole reversion, etc. But for now, not caring about that too much. And then we just do crates. I'm too used to write create. So from those numbers, by the way, are one indexed, right? So we need to be aware of that. Crates from is -1. And then, so from this from, we take one. So we do pop. I wonder what is this? What's the type of view? Show me a type. Unknown. Of course, because it's generic, we need to do this, right? I think. Okay, let me quickly look this stuff up. I think, or maybe it just needs const n. Something like that. Okay, let's look that up. Const generics Rust. Rust by practice. Implementation const and you need to say the type of it, of course. So this is your size. Why are you not satisfied still? Gosh. Do I need to say it here too? Syntax error. Compile time constants. Compile time variable. Expected function argument. Oh, maybe I'm just stupid and I need to do it here. Yes, seems so. And I guess here I don't need to redefine it. Okay, we're getting closer. Now, what don't you like? Yeah, I don't. Well, actually, creates. We can already say that. Cannot index into value of types. Yeah. State. It's not an iterator. In 1 to 1, 1 2. Okay, it should work, I think. Or will it? Oh, well, we will find out. Cannot move out. Well, we don't need to move you out. We just need to pop. And we need to unwrap because we assume that we always get a correct number of things. So that should be a char. Good. And then creates state to, again, -1 because indexing. And we just say push. Push will to the back of collection. And pop will take from the front or from the back? Last element. Yeah. Okay, so we will need to actually write it in the order. Let me quickly check. It was ZN. Okay, so we actually need to write it in that order. ZN. Okay. let's redo it. Shit. And this thing, when I copy it, fucks it up. So it was actually ZN. Okay. No, you go here. So, Z, N, and then M, C, no. Pop from the last thingy, M, C, D. Yes, I actually did everything correctly. I'm just stupid. So we pop from the here, and we then put it here. Okay, good. Wrong alarm. Push value, push X. And that seems to be it, to be honest. And then we can do part 1, which then will be just const new size. It accepts creates as reference. Then it accepts moves also as reference. And what it will return? It will return something. I forgot already what we need to return. And on top of which, I think we can do pick. So you could combine this together. So we can do pick. And that will be done as string, right? So for actually, since moves is in, so we already kind of solved it, right? So creates to move, creates moves, new creates, and then for create in. I think we can now iterate, right? For create also reserved word. Okay, in new creates, will it work? Into iterator. Let's just do iter. Will it work? No. Of course, yeah, I don't care about that for now. Can I just do this? Can I do the slicey thing? Cannot index into value of type creates. Oh, of course you cannot, because I put it inside a struct. So state. Good. And we say let mute answer is a new string. Answer push. And then we can return this. What don't you like? Consider the reference in the borrow. Does it? It returns the borrowed char. Of course. Okay, that's good. So now we can do this. And then we can do P. Of course, test P1. This creates moves. Let test answer. Assert equality test answer empty, so it fails. And let's see if it did this. DCZ. So let's see. CMZ. Huh. Zien. Okay, let's do some debug printing. How to say it? Maybe I messed up here, I think, because ranges. Let me just quickly check it, because I think I really messed up here. CMZ. Yes, I messed up in my indexing. So Julia is one index, right? So indexes start from 1. Rust and Python are 0 indexed, and Elixir also 0 indexed, I guess, but you rarely use indexes there because you normally use recursion. And in Python and in Rust, the second part of the range is always exclusive, and in Julia, it's inclusive. So that makes it always very fun with those off by 1 errors. So CMZ, right? Let's do CMZ now. We, by the way, can remove no capture and just do this. And now our test pass. Okay, now the annoying part. We need to encode our normal input thing, right? We'll do the same thing here, right? So, oh man, that will be a lot of fun. And why do you, okay, good. Q, I think it's really out of formatter is messing stuff up. BQC, right? RQWZ. So we start from the bottom and we move to top, so. So we can just copy this whole thing essentially. But that we will need to change. And let's maybe do it like that so it's a bit easier. I will do proper parsing, but first let's solve both parts. And then see if I will still do it on stream or if I do it afterwards, and we'll do a review next time. Because I don't want to make it too long, and I think we already at 42 minutes. Oh my god. Okay, RQW, that, this is torture. B, M, R, L. So at least we can quickly check it. Oh, and those are, oh, by the way, that's good that I didn't try to do like some kind of uniqueness encoding here, because the letters are of course repeated, which makes it even funnier. So we're done with 3. So this is 4, 5, 6, 7, 8, 9, right? C, Z, H, V, T, W. C, Z, H, V, T, W. N, V, J. Z, Z, H, P, N, V, J. H, N, P, C, J, F, V, Q, T, J, T, R, W, Z, S, C, J, M, N. you know, if you play Elden Ring, there is a part where you need to kill a dragon, which doesn't really fight back, but which has a lot of health, and if you try to do it on stream, like many people did, that becomes exactly that exercise I'm doing right now. You feel very dumb when you do it, believe me. So NGB WQFP CGMNBWZP SQ. Let's just pray that I didn't mess it up. And then for moves, we will do this. We will say, yeah, fs read to string unwrap. Oh, and actually, you know what? For now, let's just do, let's copy it, paste it in the interest of time, and just say, rename it, but it's that. And no, it's not JavaScript. Go away. And this, okay. So we can now inputs G05 edited and crates. Why not happy about my crates? Of course, crates 9. Right, right. Okay, let's see. I think a good indication will be if it fails, we know that we messed something up. If it doesn't fail, we know that stuff is working. So creates and moves. And of course you want references, right? Yes. Let be one answer, and then we print then part 1. I think that should already work. Let's run it and pray. Panicked. No such file or directory. Inputs. Oh yeah, they are in subdirectory, of course. Okay, let's hope that. Ta-da! Okay, we didn't mess up the input thingy. Let's see part 2. Oh man, sorry. So Samat was currently writing on the side of the crane, and you quickly wipe it away. The crane isn't crane move at 9000, it's crane mover 9001. Oh, it's over 9000. The crane mover 9000 is notable for many new and exciting features: air conditioning, leather seats, an extra cup holder, and the ability to pick up and move multiple crates at once. Again, considering the example above, the crate began in the same configuration, moving a single crate from pick up and move multiple crate. Ah, okay, now I understand. Moving a single crate from stack 2 to stack 1 behaves the same as before. However, when you move 3 crates, those 3 moved crates stay in the same order, resulting in this new configuration. They retain the order as well. So now, from stack 1 to stack 3, stay in the same order. Z and NG. Great. So, alrighty, makes sense. So instead of moving one by one, we now move everything together, and the order is preserved, which means we need to say, oh. By the way, let's write it down, and then we can add a test as usual for this. So now we have do move to Now, instead of doing this loop, we need, can we like remove slice in Rust? I think we can. So let's do array Rust slices, or like vector, vector Rust slices remove. To remove, well, I don't want first n, I want to, you can do drain. Oh, I think I never, I know I use this method, but sorry, let's make it larger. Range. Oh my god, this is magic. Keeps immutable borrower. Rust is so beautiful, man. So, so from this, instead of doing pop, we can now do train. And that takes a range. How do I pass the range? I just can do this. So I kind of can say, so it will be like, let's say, first index, last index, right? And first index 2 and 3, train 1, 2. What it takes? It takes our range bounds, use size. Okay, let's see what range bounds is. Start bound, because maybe I can do some, start index bounds. So we can do like, can we do negative indices here? I don't think so, probably not. Use by range filters, CD. But we can at least just do start index, right? So we just take source create, and then from source create length we take 1 minus, right? It will be then just minus move num. I'm not sure if that, maybe -1 is needed here. We will just find it by experience. And then we can say, this probably should be mutable, right? Yes. Source create, let's say drain, start index. And this is like this. We get the elements. This should be an iterator. Yeah, it's train of characters. Then I think we can do like append, right? Append, it only works on other vectors. Can I do like some kind of other concat? Concat flattens the slice of the into a single value. No, that's different. Append chunks, concat, extend. What does extend take? It takes, I think, only one element, right? Extend from slice, extend from within. Man, with the content of an iterator. Oh yeah, that's what we need. LMs. Right? What don't you like? Cannot move out, a non-copy array. Take immutable reference then. Cannot borrow. Second mutable borrow occurs here. Oh man, do we need to collect it? That kind of sucks. But yeah, it maintains the borrow to optimize drain, which means if you try to borrow, but I wonder, because it's a different vector. Maybe it just gets confused because we are, let me try something. Let's say target create. Maybe that will help it. State. Well, I don't need you to move out. I want a mutable reference to it. Oh, you don't like? Okay, well, that sucks, but let's just do it then, I guess. Let's collect it into vector. What? You should be able to do it. Be smart. Okay, would have been nice if we can do everything through iterators, but for now, we can do that as well. And we can then try to test part 2, right? Oh, well, actually. Oh yeah, we need also to write a function for part 2. So we can simplify it later on. For now, I will just do this. I don't try to be super fast, but still it feels nicer to make it faster. Now it should fail than doing it slower, right? So, oh no, not cargo run, of course, cargo test. So it should be MCD. And our thing was saying MCD. So we know that this is correct, which means we should be able to solve our thing now. So that we already have. Just say P2, 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 P2. And that's our answer, it seems. Ta-da! We solved it. Alrighty, it was an hour. I think I will break here. I will write the proper parsing code later and we will review it in the beginning of next stream. I think I will do a stream probably on Wednesday. So yeah, we will do review of parsing logic here, and then we will also probably look at the day 6 solution, and then we will do day 7. Yeah, shall we do a quick refactoring run here? Nah, we'll do it off the stream. Anyways, thank you for watching. Don't forget to like and subscribe, and I will probably see you on Wednesday with more advent of code. Let's see which language we will be using next time. I think for the first stream with Rust, that was actually quite nice, and I still remember it quite well. Well, I actually also wrote it just recently, so would have been weird if I already forgot everything. And new const generics are cool. It was pretty easy to start using them. Alrighty, see you. Bye-bye.